Hello students, welcome to the session of machine learning. Now we are going to discuss a topic, linear regression. So what is linear regression? This regression analysis describes the relationship between two or more variables. These variables, one or more, may be dependent variable and one or more may be independent variable. But coming to linear regression, we shall have only one dependent and one independent variable. So the regression gives a model that is a function that describes the relationship between dependent and independent variables. The dependent variable, also called response variable, and the independent variables, also called predictors. Let us see the example, income and educational level. So the educational level here may be considered as independent variable and income is dependent variable. How? Because in general, not always, in general, if the person is highly qualified, their income may be more. Less qualified, qualification, less income. Okay, except in the field of business, but generally this relation may be considered as like educational level independent variable and income dependent variable. Similarly, the demand of electricity and the weather condition. So weather condition, if it is hot, the electricity consumption may be more. If it is less, then electricity consumption may be less. But there may be exception in cold weather, like cold countries. In cold countries they have room heater, so relation may not be good enough, but in general, in case of our society, the demand of electricity may be depending upon the weather condition. So given the weather condition and electricity, we have to construct a model so that in future, having the weather condition, we can predict what would be the corresponding demand of electricity. In fact, there are some applications that based upon the electricity, okay, some more kind of prediction can be made in the society. In simple regression, generally we consider only one independent and one dependent variable. Coming to multiple regression, the number of independent variables may be more than one. Look at this scattered plot of dependent and independent variables. Having the data, we are going to predict a line which should be most suitable and such that the total sum between the estimated dependent variable and actual dependent variable should be as low as possible. So here the predicted variable, okay, will be available on the constructed model, that is nothing but a line. Or here let us say so our model here is nothing but a line and a generic equation of line, this is y cap, y estimated is equal to b naught plus b1x, as we have seen in coordinate geometry, y is equal to mx plus c. So same y is equal to mx plus c may be written as, here c is b naught, that is nothing but the intercept on y coordinate, and b1 is the slope of the model, slope of the line. So the output of the simple regression fits a straight line to the data. So that once we have a new independent variable, we have to predict the corresponding dependent variable. How? Just you put this x in this equation in place of x, and you will get y. Once we found the constant terms b0 and b1. So our purpose is to compute these parameters b0 and b1 in terms of given x and y. So the predicted value of dependent variable, that is y, may be little different or may be displaced with respect to the actual value of y, and the difference between two is considered as the error. Similarly, this error may be associated in each of the y corresponding to x. So for each y in data set, let us say we have x. So in this x, we have x1, x2 and xn, and also we have the corresponding y, y1, y2 and yn. So in each of the y, the corresponding x is there, and there is a associated error, and this associated error is assumed as random and normally distributed, having mean the expected value 0, and there is a standard deviation sigma epsilon. So this error associated with the difference between actual y and this is estimated y, the difference between two is the error, and this is randomly normally distributed. So we have to construct a model such that the total sum of this error should be minimum. So finally we are going to compute the parameters, the intercept and the slope, using least square estimation. That is, first we compute the error between each y, actual y minus estimated y, and take the square sum of this error. So we have to minimize the square sum of total error. Why square? Because if we do not square, the total sum, the total sum may be 0, because some error may be plus, some error may have negative symbol and positive symbol, and they may neutralize each other. So the total sum, most of the error will be neutralized by themselves and will not get the actual value of error. That is why we are squaring it. So the error term, total error, is equal to sum of actual y and estimated y square. Now we have to compute the parameter b. Let us consider as a vector b0 and b1, and this we shall try to compute using a matrix form for the ease of computation. So generally a vector is considered as a column vector, and let us say all beta x and y are vector of same length. So before going ahead, try to understand this transformation. Sigma of xi square is equal to x transpose x. How is it possible? So let us try to see with an example. We have x, that is x1, x2, xn. Similarly, we have y, a column. A vector is generally represented as a column vector, y1, y2 and yn. So sigma of xi square is nothing but we are squaring each term of the vector, that is x1 square plus x2 square to xn square. Same thing if you do like x transpose x, so that is x1 x2 xn, matrix multiplication x1 x2 xn. So if you multiply the first row first column, you will also get xn square plus x2 square xn square. So both are giving same expression, and that is why we can do here sigma of xi square is equal to x transpose x. Similarly, if you do sigma of xi yi, so that is nothing but multiplying these two vector element wise, so x1 y1 plus x2 y2 xn yn. The same we may get by doing x transpose y, so that is x1 x2 xn y1 y2 yn. So if you multiply first row first column, you will get x1 y1 plus x2 y2 xn yn. So both the expression giving same result. So here sigma of xi yi is equal to x transpose y. This expression we are going to use in next slide in order to compute the parameter beta. Now coming to the third, if there is a matrix, both beta and x vector, if you multiply and if you differentiate with respect to beta, or x transpose beta differentiate with respect to beta, you will get x. How? So let us say we have two vectors. So here beta and x having same length. So let us say our beta is beta naught, beta 1, beta n. So if you multiply beta transpose x, you will get beta naught x1, okay, or let us say beta 1 x1 plus beta 2 x2 beta n xn. Now if you differentiate this with respect to beta, so this is nothing but first you differentiate this with respect to beta 1, then you differentiate with respect to beta 2, then you differentiate with respect to, okay, so this you can write like is equal to beta transpose x beta 1, beta transpose x, beta 2, and dot dot, and differentiate beta transpose x, beta n. So you will get, if you differentiate this expression with respect to beta 1, you will get only x1. If you differentiate with respect to beta 2, you will get only x2, and so on. So you will get x. Okay. So here if you differentiate this beta transpose x with respect to beta, you will get x. Similarly for this, and this also you can verify in same way. Okay, this is left on you as assignment, provided you consider x as a symmetric matrix. Okay, and you verify whether you are getting or not. So these expressions we are going to use in next slide. So we had the expression total error is equal to the total sum of squared error associated with the regression line. The same can be written as this. Okay, here you may consider, okay, so xi is equal to, as there is a beta naught, means it is multiplied with 1, so you consider 1 and you consider the first, coming to here, you may consider the ith row as xi. So if 1 and xi, it is nothing but xi. Multiplied by b. So our b is here. So if you multiply ith row and b, you will get beta naught plus, or here you may consider like b naught, and this is b1. This is all about different in terminologies. So ith row, and if you multiply b, so you will get b naught plus b1x, b naught plus b1xi. So this can be written like this. And as there is a square term, so also we can write like this, that is only for ease of computation. Now look at here. So this came from this expression, sigma of xi square, you may write like x transpose x. So let us say this is our x. So sigma of xi square is equal to x transpose x. Okay. So but you may be confused that how it became, here it is ith row only, but here we have written the complete x, complete matrix x. Okay, here is the x. As there is summation, so it is applied on every row, every observation of x, for first row, then second row, third row, like that. So doing so, like here maybe first x1 b minus y1, then x2 b minus y2, x3 b minus y3, and so on. So all together we will get x b minus y. Now you decompose the transpose, will come inside. So x b whole transpose is equal to b transpose and then x transpose. Like here you may consider like there is a standard formula, a b transpose is equal to b transpose into a transpose. Okay. Now you try to multiply these two, you will get b transpose x b like this. Again it is same, but these two are combined as one expression. So b transpose x transpose y is equal to y transpose x b. Okay, both are equal. I left on you to verify it. Just take the example x y b given. Okay, having these three matrix, one is here, one is here, and one is here, and try to verify whether both are same or not. So both are same. Now this is our final expression of total error associated with regression line. Now we are trying to differentiate this with respect to b, with respect to the parameter that is b naught b1, and we are equating to 0. Now you may ask that why we are differentiating and equating to 0. You might have studied in maxima minima that if there is some function, so the maxima point or minima point, everywhere, all these points, the tangent, the slope is parallel to x-axis, that is slope of each of these points equal to 0. So in order to find out maxima or minima, okay, we have to differentiate the expression with respect to the unknown parameters and equate to 0 in order to get those points. Further, you can make double derivatives in order to see whether it is maxima or minima. Okay. That is why we are differentiating and equating to 0. Now from this expression we got b is equal to x transpose x inverse multiplied by x transpose y. So this is our expression of parameters in term of x and y, because x and y are given and b, the parameters of the line, that is here b naught b1, is not known. So we have to compute these parameters in term of x and y. So here x, y all you consider as matrix and compute this in order to get this parameter. So once you have this parameter b naught b1, then you got the line. Once you got this line, that is nothing but the regression model construction is done. Now whenever you get a new x, you predict the corresponding value of y. So this is how we computed the parameters of the linear regression, and this way we constructed the model. So our linear regression model is done. Okay. Now in next session we shall meet in order to discuss some of the performance measure of the regression model. What are the different performance metrics, like sum of squared error or coefficient of determination and so on. So in this session we are stopping here. So as a summary of this session is how we have computed the parameters of the regression line, and so we have constructed a linear regression model. Okay. Okay, thank you.